discussion session. Any questions from the audience for the two speakers? Please feel free to raise your hand. Oh, there's a question from, I think, Nabi.
Hello, hi, this is
Shu-Heng. Yeah, okay.
Hi. I have a question for the second talk. So in one of the slides, you mentioned a U1 one-form symmetry. What was that system and what was that U1 one-form symmetry?
Let me see. One of the slides I mentioned a U1 one-form symmetry. Are you?
There's a U1 with a superscript 1. Yeah, that one.
Okay, so for such a system, we are still consider the discrete one-form symmetry. For example, the Dn one-form symmetry. When the n is larger than 4, we know that an anisotropy is irrelevant on the RG. So in the IR, it is a U1 one-form symmetry. U1 one-form symmetry, but in the UV, we can start with finite symmetry in order to make the categorical symmetry well-defined.
What's the relation between the U1 one-form symmetry and the U1 zero-form symmetry?
You mean you're asking the notation? Probably I shouldn't write in a cross product. They are dual to each other, so it's not a simple product of the two symmetries.
But that's the thing I'm confused by. So if you start with a Zn zero-form symmetry in 2 + 1D, and you gauge that Zn zero-form symmetry, in the gauge theory, you will have a Zn one-form symmetry. And I assume that's what you meant by the inexplicit dual symmetry. So that story, I think I understand for Zn. But for U1, it's fundamentally different. You start with a 2 + 1D system with a U1 zero-form symmetry, and you gauge that U1 zero-form symmetry. In the gauge theory, there isn't a U1 one-form symmetry. There's a U1 zero-form.
Yeah, and that's
pretty much Dn and U1.
Yes, indeed. The Dn and U1 are quite different. If you look at for example, the picture is different, right? So the Dn, the one-form symmetry is well defined for the domain O, right? In the original model. But for the U1 case, it's quite different. The defect would be vertex instead of the domain O. So that's pretty much the reason we start with finite. Our system should be with the finite symmetry that's a well-defined starting point. The only thing we want here we need is in the IR, the anisotropy for the Dn is irrelevant and can be embedded in a U1 theory, and it brings us the convenience to doing a calculation using continuous U1 theory. However, conceptually, we are restricted to this finite the one-form symmetry.
But either on the lattice or in the continuum, either in the UV or in the IR, there's no U1 one-form symmetry in any of these systems, right?
I think Shu-Heng is right. Actually, yeah, we probably should have said that just a U1 zero-form get enlarged. Sorry, a Zn zero-form. It actually enlarged to emerge in a U1 zero-form. But actually, we shouldn't say the dual of Zn one-form is enlarged to a dual U1 one-form. Yeah, for the reason that Shu-Heng mentioned. Yeah. But you know the result probably does not rely on this, but you know
right.
Yeah, that concept should be clarified. Yeah.
Okay. Thank you.
That's right. Yeah, no problem.
Okay. Meng also has a question.
Hey, so sorry, I have a question for Kevin. Excuse me. So Kevin, in your very last slide, you mentioned that there's example of non-abelian fractal model in your recent foliated field theory. Can you briefly say how these non-abelian theories arise?
Yeah, our potions here actually he should probably take over.
Okay,
so the construction is basically coupling a non-abelian gauge theory, just ordinary non-abelian gauge theory to some foliated gauge field. plus the construction.
So you mean non-abelian like global, sorry, zero form gauge field? Is that what you mean?
Yeah, just like yeah, just take a non-abelian gauge theory with ordinary gauge field, like one form gauge field, and then couple it to Fourier gauge field. And in that way, you can get some like non-abelian fractals.
Excuse me, sorry for interrupt, but related question. But the reason it's non-abelian is that because the two symmetry does not commute, or the two gauge symmetry generator does not commute, or something like that.
I mean, just take a non-abelian gauge theory like DA gauge theory or some SU2 gauge theory, and then you couple such gauge theory to some foliated gauge field.
So the TQFT, the ordinary anti-symmetric tensor TQFT is already non-abelian in your setup. Is that right?
I think what Ocean said is that you take an ordinary one form non-abelian gauge field, right?
Yeah, you take an ordinary non-abelian gauge theory, and then you just couple it to. So, for instance, if you take SU2 gauge theory, then it has a Z2 one form symmetry. Then you can use the Z2 one form symmetry to couple this SU2 gauge theory to a foliated gauge field.
I see. So does it mean that in that case, for example, the spin 1/2 would become the mobility will be restricted?
Right, the mobility will be restricted for this fundamental Wilson line SU2.
I see.
You can also consider like finite group example.
Okay, but you need maybe a center that can couple.
So it's not necessary actually.
Just a normal subgroup, or
yeah, just a normal subgroup.
Okay, and is it related to this hybrid fractal model in any way?
Oh yeah, so this field theory can describe these hybrid fractal models.
Okay, all right, thanks.
Another question from Yiju.
Yeah, thanks. I have a question for Xiao-Chuan. In your ODO for the subsystem symmetry case, at a quantum critical point, the Wilson line behavior in the dual language is exponential minus ln x ln 1. I wonder, is it derived from the embedded U1 symmetry, or this also applied for Zn or Z2 symmetry?
Let me go to that slide to be precise. You're asking
yes,
here?
This one,
or?
Yes.
So the critical point is derived using a continuous theory, using a U1 version. And in the gapped phases, we can do perturbation. We can just do perturbation.
I see. And also for the quantum critical point, it's in the previous and the dual side, it's something like subsystem symmetry breaking phase versus the paramagnetic phase. And some perhaps simulation shows it might be a first order instead of a critical point. I'm not sure in your theory whether one can demonstrate there exists a second order phase transition or not.
You mean precisely the theory here? You mean U1?
Yeah, but discretize it to Z2.
I see.
Discretize theta to Z2.
Yeah, maybe I can clarify a little bit.
Yeah.
So indeed, for the just the Z2 case, the quantum Monte Carlo, well, and some other shows that it's a first order. Actually, that's why actually we should have said that this is a fine-tuned criticality. You have to fine-tune one more parameter probably to get this critical point. So it's more like a multi-critical point in this case. So in 3+1D, that gapless phase is more stable. Well, because we don't really need to fine-tune much to get the gapless photon phase. So I guess it's should still hold with a subsystem symmetry. Yeah, but you are right. In 2+1D with just Z2, numerics shows it's a first order. So we need to fine-tune one more term to get this gapless point.
Right, thanks.
Yeah.
Next question, Dominic.
Hi, so I have a question for Kevin. Can you compute things like for example, ground state degeneracy directly from these forwarded field theories?
Yeah, in the new paper with Poshan, we do the ground state degeneracy calculation for a few of the models.
I guess I'm a little
so yeah,
confused in the sense
so
that the ground state degeneracy seems to like depend on this discrete number of layers, but the formulation doesn't quite have this discrete structure yet. How does that work?
yes, exactly. So at first it seems like you should get an infinite number of ground state degeneracies because the layers are kind of infinitesimally spaced. If you want to get a finite number, then you have to add some sort of a cutoff. And if you add that cutoff, then you can get a finite number. So you have to add an additional cutoff in order to get that finite number.
So there's some very precise way to formulate that?
I don't know how precise it is exactly. Maybe Poshan can comment on what he thinks about it. We have a prescription, but I don't know about in full generality how it works out.
So I have another question, either for you or just for the audience. You know, for regular field theories, regular topological field theories, not the forwarded ones, you know, mathematicians consider the physicist's definition in terms of actions not to be rigorous enough, and so they instead define things in terms of functors and borders and category, etc. Is there any hope, or is anybody trying to do something like that for the forwarded field theories?
I think as an initial work, Michael Hermele and Shreya talked about the fusion in fracton theories, in these foliated fracton theories. And instead of a fusion group, they had to use a module. That would perhaps be the first step, because now you have, once you've got this structure, maybe then you can talk about braiding in some way. I think that's rather open. Is that kind of getting at what you're asking?
Not exactly. I mean, I was talking about not the structure of excitations, but just the definition of a field theory in terms of functor definition.
Dominic, do you mean like you consider manifolds with foliation structure and think about the Bodism,
yeah,
functor of this Bodism category to some target?
Yeah, that's what I mean.
Okay. Yeah, that's interesting question for sure.
I have two questions, if I may. So one for Kevin, maybe you can see me. Can you hear me?
Yeah.
I can hear you.
Oh, one for Kevin. So you mentioned that your fields are discontinuous away from the plane on which we have a standard field theory. And these fields appear as sources for the bulk fields. So they will necessarily induce discontinuities also in the bulk fields. But the same bulk fields also couple to the orthogonal layers. So that would induce discontinuities also there. So do you have any control in the setup that you have about what is and what is not continuous? The reason I mentioned that is that in our approach, there were clear rules which discontinuities are or are not allowed, but it was not broken so simply into layer fields and bulk fields.
Right. So the new paper with Poshan, we're much more careful, and we very explicitly say which fields are allowed to have certain kinds of delta function singularities, or which fields can have discontinuous discontinuities.
And if you integrate out all the extra fields to go back to, say, your original BF description of X cube model, do you end up with the same rules about the discontinuities as the one that Truhan and I had, or is it a different rule?
That's a good consistency check. I didn't explicitly calculate that. I don't know if Poshen did. But yeah, I agree that you should.
I think Shuhan mentioned to me that the theory have the same kind of discontinuity or singularity that he discussed with Nati.
Oh, I only commented on the layer fields, but I'm not sure the whole systems do. Actually, I think in your paper, you guys have a very nice and clean discussion about how the layers field allow different kinds of discontinuities. But I think there were not so many discussions about the discontinuity for the bulk fields. And I think that's what Nati was mostly curious about.
So that's the first thing I was curious. But the second thing is that the singularities in the bulk fields are going to feed into additional discontinuities on the layer fields. And I'm not convinced that this whole, so you can just declare that nothing is continuous and that's the end of it. But if you say that there's any sense of continuity, I think there's something to be checked here. Let me move to my other question about which is a question for both for the next speaker, but also more generally. When we discuss duality, we give two equivalent descriptions of the same system. So the global symmetries of the system cannot change by performing a duality. Then there's something else you could do. Take the system, engage part of its global symmetry. And if you do that, the global symmetry that you gauged is gone. It's no longer a symmetry. And instead, there might be a new symmetry. And the comment that Shuheng mentioned earlier is along these lines. But it's very important that you cannot have both symmetries at the same time. So that's why I'm very confused when people talk about the symmetries and the dual symmetries. So for example, in Ising model, there's only one Z2 symmetry, not two. There's no other Z2 symmetry. And you should definitely not consider anomalies between them and so forth. The spectrum of the theory has only one Z2 global symmetry, not two. And this comment propagates through the entire talk. So it's not just the Ising model, but throughout the talk.
I think whether the symmetry is there or not depends on how you define whether there's a symmetry or not, right? So, but I think either in the original Ising model or in the dual Ising model, there are some well-defined quantity that we can define, and that quantity can have different scalings, and that there's no ambiguity to say that the different scaling behavior have give us different phases. So I think that's all we can tell based on.
No, I'm very confused. In the end of the day, we have a Hilbert space and a set of operators in a Hamiltonian. And we could ask, is there a symmetry operator which is defined by an operator that commutes with a Hamiltonian? And then we can classify the Hilbert space according to representations of symmetry. This is independent of whether you use this set of variables or dual variables or whatever you do. There's one global symmetry to the system. The system has one global symmetry. And there's no ambiguity in what the global symmetry is. So, and in particular, the Ising model with the critical point has one and only one Z2 symmetry. There's no other Z2 symmetry.
Yeah, Nadi. Actually, yeah. This is also my early response when I saw the categorical symmetry. I got confused for a long time. Indeed, actually, the Z2 Ising should only have one symmetry. But actually, I think in Wenjie and Xiaogang's paper, they actually did well. They changed the Hilbert space. That's actually an important thing. For example, well, so let's probably simply think we just talk about 1+1, the Ising model. I think they changed the Hilbert space. For example, they can actually consider only the symmetric subspace of the original Z2 symmetry, which is the orbifold of the original Z2 symmetry. And they also consider the situation where they enlarge the Hilbert space of the dual model. So that means that actually when you enlarge the Hilbert space, actually that model is not really the transfer field quantum Ising model anymore, because the physical states are different. So in that enlarged model, actually you do have the Z2 cross Z2 symmetry in the conventional sense.
Only the other Z2. So first of all, let's get references straight. This whole categorical symmetry, if I understand correctly, had been done earlier by Shu-Heng Xiao and collaborators. That's the first. Let's get the reference straight. Sometimes it helps. And they actually got it completely right in their original paper. The system has only one Z2 symmetry, not two. Then there is another system. This manipulation that you discussed, take only the invariant states and enlarge it and so forth. This is synonymous with saying there's a global Z2 symmetry and we gauge the Z2 symmetry. This is just synonymous to it. In the high energy physics, this is called obifolding the system. But this is nothing but coupling the system to a Z2 gauge field. And it's important that this is a different system. So
true. Yeah, right. It's true. I mean, yeah, I totally agree with that. I'm just saying that. Okay.
Imagine we consider one free fermion in 4 dimensions. So it has a U1 global symmetry. We can gauge the symmetry by coupling it to a U1 gauge field. By that point, the original U1 global symmetry is gone, and there might be some other magnetic one-form symmetry, etc. But this is a different system, and there is no system in which you have both.
Yeah, I know. I mean,
and this was done completely right. I forget who the other author. These are Shu-Heng and.
Sure. Let's not. Well, yeah. I mean, frankly, I have not read Shu-Heng's paper, so I'm not sure. But I think I got what you mean, how it was formulated in Shu-Heng's paper. I'm just saying that by orbifold, my understanding is that you gauge the system, but you don't add any dynamics of the gauge field.
Yes, you do.
Actually, okay, yeah, fine. So actually, my understanding of Wenjie and Xiaogang's paper is that actually when they change Hilbert space, they do gauge it, but they don't change dynamics. They don't add dynamics of the gauge field.
Yes, they do add it. No, I'm sorry.
Really? I thought by changing the Hilbert space, the criticality is the same universality class. That would mean that the dynamics does not change. Maybe I misunderstood. I should go back to read that. But my understanding is that.
You're right that the critical point is the same critical point, but the collection of operators you study are different. In the first,
sure, but the operator algebra is more like a math thing. Yeah, so I'm wondering whether gauging invariant operator, if I calculate correlation function for example, I mean calculate anything with the gauging invariant operator, is there any difference between gauged or not gauged?
It's completely different. It's complete
for gauging invariant operators.
In general, the obifolded theory and the original theory are not the same. Some operators have the same correlation functions, but as theories that are different.
Yeah. So yeah, I'm asking about so if I just consider the operator, whether you gauge or whether you don't gauge, they are both gauging invariant. If I calculate, for example, just calculate Ising correlation function, right?
Yes.
So is it going to be the same or different in Xiaogang and Xiaogang's paper by taking by changing the Hilbert space?
First, there is an Ising model, and there's the original Ising model. There's another model obtained after gauging. These two models are not the same.
I know. Yeah, I mean, some operators are eliminated because of the gauge,
and others get in. And it is a peculiarity of the Ising model that the original model and the new one are not the same, but are similar. But the models are really different. For example, duality exchanges the two sides or the two phases. And if you do the gauging, then you flip it again. So if you consider Ising and the gauged Ising, the broken phase and the unbroken phase are swapped. It's not the same model. And
yeah, right.
Very degenerate case, so you don't really see. In other cases, the spectrum is completely different. The spectrum is completely different. The correlation functions are completely different. These are just different models.
Well, spectrum is different, but actually, if I take a model 1 and I remove some states which are not gauging invariant, so is the spectrum going to be the same as model 2?
Yeah.
Yeah, then that's what I meant by some quantity are the same, right? So if I just calculate the restricted number of operators, they are still going to be the same.
Yeah,
and
but
actually,
thank you. This is very misleading. Let's start with the 0-point function. So I'm not even putting correlation, just the 0-point function. And I'm computing the correlation function, the partition function with no insertions on the torus, the answers are different. You get different answers. The torus partition function is one number.
That's true. That's true. Yeah, I understand the partition function will be different. Let's see.
I think the point you try to get is that there is a lattice model written down, I think, in Wenjie. Wenjie actually typed a message. Her audio somehow doesn't work. That there's a model you can write down. It's not a tensor product Hilbert space. It's essentially the edge of a toric code. The model you can write down that has both symmetries explicit as like true global symmetries on lattice.
I agree with that, but that's not a two-dimensional field.
Yeah, it's not a 1+1D Ising CFT.
You can change this, you can change the system. There's another system which you can study, which is really 2+1 dimensional.
No, this is still 1+1. It's still 1+1. It's just a Hilbert space is not tensor product. And you have both symmetries there in the model.
Well, I mean, yeah, certainly I understand the word categorical symmetry means that it's the symmetry of the anions in 2+1 dimension. I'm just wondering that whether by doing calculation 1+1D, we can compute some desirable thing that we are more concerned about in 2+1D in one higher dimension. For example, some calculation. Well, so for example, if we really want to study 2+1D topological order and want to study its boundary, but actually some quantities can still be calculated with just a 1+1D transfer quantum Ising model. Yeah, I think suppose the quantity calculated can be translated in 1+1 dimensional framework, then well, I mean, maybe there could be a way to generalize the concept of categorical symmetry to 1+1D. I mean, that was actually the language used in the Xiao-Gan's and Wenjie's original paper. Maybe actually involves some conceptual clarification there. Yeah, but I'm mostly concerned. I'm mostly interested in calculable quantities here. I think maybe the concept needs to be clarified more. You know, in the lower dimensional field theory. That I do agree. Actually, it took me a while to make myself comfortable with it. But eventually, I feel that if we only look at a restricted number of quantities, not those which actually cause trouble, then actually they are a set of operators or quantities which are the same, whether we consider orbifold or not, whether we consider whether we put a system in a 1+1D system or put a system at the boundary of 2+1D system. For example, universality class is obviously the same. You know, all the singularities in the thermodynamic sense are the same. So these are the quantities which I want to focus on.
This is not true. This is true when you discuss singularities, you discuss deforming the system by some operator. But the set of operators that you can deform the system is different in the two cases.
No, but suppose I only look at the subset of operators which are ubiquitous, which are the same for the two series. So for example, I just tune the energy density, right? Like the quantum critical point is tuned by changing the Hamiltonian. So by changing the, for example, energy density or the local Hamiltonian density in this form, I tune the quantum critical point.
I understand it very well. So in the example of Ising, which is actually misleadingly simple, and that's why you don't see the picture. Ising at the critical point has three kinds of field. One, epsilon and sigma, using conformal field theory notation. Now, the restricted theory has only one in epsilon. Because in the other theory, you throw away sigma and you get instead the disorder operator mu. So you have, roughly speaking, 2/3 of the operators. In other more interesting examples, you throw away many more. And the set of operators that you keep is a much smaller fraction of the set of possible local operators. Now, it is true that the correlation functions of these local operators are the same in the two models when you consider the system on R2. But if you put the system on a torus, with or without insertions, it's already different. And if you consider the other correlation functions, they are also different. So for example, it could be that one model has a relevant operator that the other one doesn't. And therefore, if you start from some lattice model and you ask, is the system stable and so forth, one of them has an instability and the other doesn't. So these are really two fundamentally different models, and they also have different symmetries, and it makes no sense to consider both of them simultaneously.
Well, I fully agree with all the statements you make. Yeah, so I think actually the reason we consider them as a lower dimensional context is sometimes it's actually more convenient to calculations in the lower dimensional context, as long as we look at the right quantities. Of course, there are a lot of quantities actually we cannot look at, or they are going to make some difference. But as long as we look at the right quantities, actually they can describe something which is as the boundary of a higher dimensional system where the symmetry is better defined, which I totally agree. In a higher dimensional system, these symmetries are definitely better defined. Yeah, right. That's all I gotta say. I mean, I fully agree with you that the symmetry is certainly much better defined in a higher dimensional context. Probably it's the same case for all the higher dimensional situations.
This is the third system. I think you're discussing simultaneously three distinct systems: the original one, the gauge one, and the higher dimensional field theory. These are three different physical systems, and they have different properties.
Yeah, they share some common properties. That's what we want to calculate, right? They share some, not all. And this subset of quantities is all we want to calculate, right? That's what we want to focus on. You know, maybe some concepts need to be clarified. What exactly these quantities are? Yeah, that's indeed worth to clarify in detail. You know.
But Zhenke, is it right that all your calculations are done in one of them, right? You don't really need to involve three of them.
Yeah, right. Indeed, we do calculation in one of them. We think, but we didn't prove that these quantities are going to be the same in all the different systems. We think we didn't prove that. I mean, but we think they are going to be the same if we take all these different descriptions or just different theories. Okay, so maybe not theory, maybe not description. There are different theories, but we think they share certain quantities. And actually, our calculation in one of the theories should be the same. I think they should be the same for all the three theories. Of course, they do have difference, you know, but we focus on the quantities which actually they are the same. They share the common quantities they share. Like in the thermodynamic sense, at least all the, for example, the specific heat in all the systems should be should have the same scaling. You know, I mean,
don't even have the same number of ground states. So if you take icing and you deform it to one phase, so in the broken phase, it has two ground states.
Yeah, I do agree with that. Yeah, so certainly I'm aware of that. I'm just saying that for some quantities, the number of ground states does not really matter. For example, if you really just want to calculate how the energy scale with a tuning parameter, ground state energy scale with tuning parameter, like the ground state energy scale with tuning parameter as like you know, some scaling dimension or some critical exponent nu. That nu really is going to be the same for the 2+1D quantum Ising model or the 2+1D quantum Ising gauge theory. You know, the deconfined phase for 2+1D Z2 gauge theory has the same critical exponent nu as the 2+1 dimensional quantum Ising theory. Yeah, so so the nu is actually one of the quantities which they share. So these are the quantities I want to focus on.
I disagree already. Some of the critical exponents are the same, not all of them.
I know, I never said all of them are the same. I only want to look at the ones they are the same. Okay. I only want to look at the subset of exponents which they all share, right? That's so as I said many times, actually, if we look at the right quantities, if we are careful about that, then actually we can get the same feature of all three theories. But certainly we should be very careful of that. I mean, certainly not all quantities are the same. I fully agree with that. You know, we have to look at the right quantities. Yeah.
I think maybe as well read Wenjie's message because I'm not sure the recordings will include chat messages. So Wenjie's message says, the system most precisely for the categorical symmetry is neither the even model or the orbifold model, but only the D2 even sector of even model or the dual D2 even sector of the orbifolded model. Hope that helps. And also there's another question from Nat.
I think it's right. I think that is right, that in the restricted Hilbert space, indeed, that neither D2 symmetry exists in a conventional sense. Yeah, I think that's right. I mean, for example, like you know, I mean, just like Nadi just said, right? So they are, I mean, you know, they are so for different theories, actually, there are a lot of things which are different. So this is the, so for example, if we talk about ground state degeneracy in the restricted Hilbert space, it's going to be very different from the unrestricted Hilbert space. So it means that if we define the symmetry as that when it's spontaneously broken, there's a ground state degeneracy, then these symmetries don't exist. Yeah, these symmetries don't exist.
Thanks, Finko. Ethan, I remember you raising your hand earlier. Do you still have a question?
Oh, no, I answered it for myself, sorry.
Okay. So, any more questions?
I had a quick question for Kevin. Is that okay? Sure. So in the abelian case, you said that when you move a mobile particle, that sort of creates a line on, that creates a planon, and that's why it's immobile. So for the non-abelian case, when you move a non-abelian particle, do you also get like an abelian planon, or is it possible to get like a non-abelian planon? Because you're saying that you're choosing some normal subgroup, and in that case, the normal subgroup is abelian.
I haven't thought about that. Have you, Poshan? I don't know if he's still there.
Yeah, I have to think about that.
I guess we'll have to get back to you. Thanks.
Thanks.
Hi, can people hear me now?
Yeah.
Oh, thanks. I want to address this question by Shu Heng in the chat. He says that this Z2 even sector is not a well-defined 1+1D system. Yes, it's not a complete UV completed system. So it does not have tensor product, so it cannot be on a lattice only in 1+1D. So one setting to consider it, of course, is to take the as a boundary theory of the 2+1D Z2 gauge theory. But as long as we put it there, we only consider the boundary dynamics. We no longer consider any dynamics from the bulk. The bulk is completely in a vacuum sector. So this gives the global constraint to the boundary.
Okay, but in any case, I think you agree that it's not a 1+1D system.
Are you unmuted?
It's a 1+1D system that is anomalous in some sense, right? I don't feel so it's fair to say that you have to have a tensor product structure to be a 1D system. It's just somehow anomalous, right?
It's worse than that. It's worse than that. It's not just an Tuft anomaly. It's an inconsistent.
Yeah, the other one is also
yeah, this whole thing was confusing in the 80s, and people got it completely straight in the 80s. There's no need to reinvent the wheel. If you just take the Ising model and you consider only the identity sector and the energy operator, and you throw away sigma, this field theory is an inconsistent 1+1 dimensional field theory. There are many things wrong with it. And we can go through that. I can give you a whole lecture about that. But this system is just inconsistent before even we get to anomalies. Anomalies is something much more subtle. Right. So
would you say that the boundary? What about the boundary of a integer quantum hole? Is that more or less inconsistent than what you're talking about?
I think it is. I'll have to think about that. It depends on exactly how you define it. If you define just the left-moving scalar, it's an inconsistent field theory. But if you take both left-moving and right-moving scalars, then it is a consistent one. The question is really whether the bulk does or does not have dynamical degrees of freedom. So you can have if you want to have in the bulk an invertible field theory, then the boundary is a consistent field theory, albeit one with an anomaly. If, however, you wanted the bulk to have dynamical degrees of freedom, then the theory is not 1+1 dimensional, it is 2+1 dimensional. So we can discuss both of them, but I think it's confusing to discuss both at the same time.
I think we want to discuss, there is a bulk, but there's all the dynamics of the bulk is high energy. So only consider the ground state of the bulk. For example, take that fraction quantum Hall. You can have some Chern-Simons in the bulk, and then the K matrix to describe is like this 1 minus 3. And then you consider only the boundary theory. And this boundary theory is actually, in terms of CFT, it's not modular invariant. So it's not gappable. But now we consider a generalization of that. So the bulk is a Z2 gauge theory in the only in the vacuum sector. Then the boundary itself is still not modular invariant.
Okay, so let's leave out issues of spin theories, because that would be besides the point. So if we just leave out issues of spin field of spin theories or fermionic theories, then a 1+1 dimensional CFT must be modular invariant. So
yes,
all the theories that we discuss here are not modular. And the reason people talk about modular tensor category, when I underscore the word modular, because the modularity is very important. So among other things, this system is not modular invariant. Now, if you put in the bulk some Chern-Simons theory, say U1, level 5, level 8, I don't care, some theory, then the bulk is non-trivial. There are correlation functions in the bulk. That changes the story completely. This is a different system, but it's not, and in particular, it's not a 2+1 dimensional field theory.
But maybe, I mean, maybe this is just a terminological issue. I mean, if you have a gapped topological phase in 2 dimensions, let's assume that the gap of all excitations in the bulk is very large, yes, and all the dynamics takes place on the boundary at low energies. So I think for physicists or condensed matter physicists, maybe would say that that's a 1-dimensional dynamics, even though, I mean, you need a 2-dimensional system to make it well defined. I mean, I think that's what you're saying.
No, that's
a terminology thing.
No, it's not a terminology thing. There's a big distinction. If you have in the bulk TQFT, I've already thrown away all the quasi-particles. I don't have the quasi-particles. I have only the topological sector. Among other things, if the bulk is non-trivial topology, then I have a non-trivial ground state degeneracy. So this is a physical.
Yeah, but I'm imagining the case where the bulk, does not have
I think
put the system on
I think the point Dominic trying to make is that indeed, actually, certainly we all agree that the bulk is important in many ways. But actually, for example, for the quantum Hall system, if I just want to calculate some physical quantity like the local density of states at the boundary, using the chiral 1+1 chiral theory, which is sick, but using the 1+1 chiral theory, we can do calculation which is correct and actually makes the right prediction.
I agree with you, Jenke, that if you view the whole thing as a way to calculate a small number of observables, I have no problem with that.
Yeah, sure. I mean, that's all I want to do, actually. I just want to calculate a finite set or a limited set of quantities, which actually are all these different theories share. So suppose we calculate something sick, that's actually going to be, it's only going to exist in one theory, but not the other. I mean, but actually those are quantities we ban ourselves to calculate.
Completely irrelevant. If you're only interested in these correlation functions, then the global symmetry in one theory or the other or both is completely irrelevant. In fact, Nat put it in the chat very, very clearly. He said that in the restricted Hilbert space, is it correct that neither these Z2s are symmetries? It just acts as the identity. And I responded to him, yeah, it's trivial. It doesn't act there. Therefore, it doesn't give you any information. So if you're only interested in these particular numbers, then the global symmetry plays no role. Now, why is, let me just answer also the issue that Dominic raised. If you have a 1+1 dimensional field theory, you have operators which are at points and you can consider their correlation functions. If the system is attached to a bulk, you should also consider operators which are point on the boundary, but they are attached to a line in the bulk. And then there could be all sorts of things that you can or cannot do if you study only the theory on the boundary, but they get different contribution depending on what happens in the bulk. For example, if all these lines that you send to the bulk start braiding, nothing happens on the boundary, right? Nothing happens on the boundary, but you're going to get different answers. So I think it's really important to know which theory you're talking about, pick a theory, stick with it, and then write all the observables and make sure that the theory is consistent. It could be one of the theories or the other, or the theory coupled to a bulk with dynamical fields. But these are different systems.
Yeah, I think that's right. I think in the future, if we do calculation, we probably should have clarify this. I mean, there are different theories. We have to be careful what we can or cannot talk about in one of the theory. And there may be some catch.
So what is
have to be careful.
So what is categorical symmetry after all this discussion? I was actually confused. What is categorical symmetry after all this discussion? I was very confused in the beginning as well.
Okay, let me say, we only want to, the starting point is still the boundary theory of a topological theory. But then, of course, if you want to be like everything consistent, you need to include the bulk. But to talk about the dynamics of the boundary, the part of the bulk that only needs to be included is those topological sectors. So, for example, this one of the sickness of this boundary theory is that it's no longer modular invariant. And our purpose is bring that out, how it breaks the modular invariance. So then you found that if you start with this and then you do modular transformation, it will be mapped to another super selection sector with another boundary. So if from Nati or high energy point of view, the best way to put it is always to consider the whole 2+1D system. That's of course make sure that you have already included everything. But from a condensed matter point of view, in many cases, we really only care about the boundary dynamics. And then if you only care about the boundary dynamics when the bulk is in a vacuum, then this local dynamics is still these Z2 excitations. That part is the same as the Z2 Ising model. But then if you want to consider other global properties of this boundary theory, then you need to include some part of the bulk. That's the other super selection sector, the global constraints coming from that. But that's how far as we need to talk about this boundary theory. And further than that, this global symmetry constraints on the boundary is what we call the categorical symmetry.
It's really a constraint and not a symmetry, or is that a bad thing to say?
Oh, sorry.
It's constraint. Okay. It's first, for sure, it's a global constraint, and this constraint is like it's actually, maybe you can think of them some projector operators, and some of the projector operators come from the Z2 global symmetry. Some of the projector operators coming from the dual Z2 symmetry. So yeah, just set of these projector operators, and they satisfy some rules. And they all inherited from some global symmetry operators.
You're saying you call it a symmetry because it's ultimately related to a symmetry in some other model, but in the specific context that you were talking about, where you consider the Z2 even sector, then it's just a constraint, but it's related to a symmetry. Is that what you're saying?
Yes, those projectors operators would be the same as you would use to describe the 1+1D real Ising model.
Right.
We just don't use the global symmetry operators, we just change them all to the projector operators.
But in the same spirit, you can also say that the system has an E7 global symmetry or some dihedral group, which happens not to act, right? You invent a symmetry which is not there, and then you project those states that are invariant under it. And I completely agree with Dominic. And furthermore, I would say that it's a constraint, except that you started your story in the constrained subspace where the symmetry doesn't act in the first place.
But it's a non-trivial constraint in the sense that in the thing you were describing, where you try to just impose some dihedral symmetry constraint, it's not really forcing the Hilbert space to be non-tensor products. So then, like, you don't. This constraint is superfluous. Whereas in the cases that Wendy is talking about, it's actually having a non-trivial consequence.
Well, it's a trivial for one Z2, but not for the other. So the Ising model has one Z2. And that Z2, we can look at the Z2 invariant sector. The other Z2 is not a symmetry of the Ising model. In fact, all the states in the Ising model are already invariant under the other Z2. So what you said is completely right. If you start from Ising model and then you restrict to the Z2 invariant operators and you consider their correlation functions. That I could accept that, but then the other Z2 plays no role in this story.
It plays. So first you do this Z2 even projection, then you check how inconsistent, what the thickness in this constraints Hilbert space. You do the modular transformation. Then you found it's not invariant, right? You will be mapped to some Z2 odd sectors, and then you do another modular transformation. Then you will be mapped to the dual Z2 projected sectors. That's how they relate. So we consider this global constraint, and we also consider this modular transformations, like to detect how non-tensor product this Hilbert space is. Then you end up with the project sectors of dual Z2 symmetries. That's unavoidable. It's always, as long as you do modular transformation, you always got all other sectors, and all other sectors are coming from the projectors of the dual symmetries. Because we want to detect how non-tensor product this Hilbert space is.
So since I'm the oldest person around, let me give some historical perspective. This issue of whether we should or should not impose modular invariance in a 1+1 dimensional CFT was very confusing in the mid-80s. And as far as I can tell, the person who got it completely right for the first time was John Coddy. And that was sometimes in the mid-80s or maybe late 80s. And I think he's definitely not a high energy physicist. You can call it a statistical mechanics or condensed matter or whatever. And he basically said, that's the end. It has to be modular invariant. And he had strong arguments why, and he derived lots of consistency conditions from it. Now, this whole discussion is about, let's relax this condition of modular invariance, get in trouble, and see how we can fix the trouble.
Mm-hmm. Yeah, we would just want to see one scenario, how this modular invariance is break. And the reason is it happens in these topological phases. And it's actually also something also could happen in fractional quantum Hall. It relates to some boundary theory. Even it's non-chiral, it's not gappable. And you still need to use the modular transformation to detect that.
But this is not really only about the CFT, right? Modular invariance, of course, is for 1+1 CFT. And I think the point is that if you only have one Z2, like in the true Ising model, and the other is identity, then the system is a tensor product, has a tensor product Hilbert space. But if you
Yes.
want both Z2, then you cannot have this as a tensor product. And maybe it's not entirely correct to call this anomaly because no, this is not tooth anomaly, but still doesn't have a tensor product Hilbert space. So
you call it non-invertible anomaly when sharing your papers, right?
yeah, but I guess
Look, this is much worse than that. This non-invertible anomaly, as Dominic said, really means that this is not a 1+1 dimensional field theory. One way of saying it is that the correlation functions of local operators in this construction are not local. You take one local operator and you move it around another, you come back to another point. Or in terms of a Lorentzian interpretation, the commutation relations are bad. Does not have a consistent operator algebra. Right? The interactions are non-local. So this theory is really sick as a 1+1 dimensional field theory. Now, you can make sense of it by attaching it to a bulk with dynamical degrees of freedom in the bulk. As you said, non-invertible bulk. That's another theory. And
I think that the operators that the sick operators will not appear as local operators in the 1+1 theory at all, right?
No, they need to be attached to lines in the bulk.
Yeah.
Bad operators are attached to lines in the bulk. And as you move them in the boundary, you take one of them around another in the boundary, you come back to the same point as you started with. So you start from two operators, you take one of them around the other, and you come back to the same point. In a 1+1 dimensional field theory, the correlation function should be the same. It depends only on the positions of the operators. There's no braiding in operators.
Right.
But you remember that these things are attached to lines in the bulk. As you take one around the other, the lines in the bulk were twisted around each other. And as a result, the answer could be different. So you're explaining the lack of locality in the boundary correlation functions is something that is sensible and physical by including information from the bulk. But this is
if you want to study the local dynamics of a one-dimensional boundary, I think you just don't include those operators, right? Is that what you're saying, Meg?
Yeah. So if you want a 1+1 dimensional field theory, take a subset of the operators such that the correlation functions are local relative to each other. So if you take one around the other, correlation functions depend only on the position of operators. So
yeah, that's what local operators supposed to mean, right?
That's what it means. Yeah.
Because now everything you said applies to the chiral vertex operators in the ordinary 1+1 CFT. If you think
I know what about the chiral vertex operator, Mark. As you know, I think I actually worked on this.
Yeah, I know. That's why
correlation functions are non-local.
Yeah.
The construction of these chiral vertex operators is that you start from something. The correlation functions are non-local in 1+1 dimensions. And you get to study them. They are very interesting objects, even though they are not local. Then you're trying to make a theory out of these building blocks. Because they're non-local, this cannot be the final answer. And you have several avenues. You can attach left movers and right movers in different ways. You can make projections. There are all sorts of things you can do with these building blocks.
Yeah.
But you have to do this step. One thing you can do is attach a bulk and keep track of the non-locality by keeping track of what operators do in the bulk. But this is a two-step process. Step one, you study the chiral sector. In step two, you're trying to construct a fully consistent theory out of it.
Yeah. I mean, the only reason I mentioned it is that these operators are not local operators. So if we don't study them, right?
So in CFT, people often study these non-local operators, and they give you conformal blocks and so forth. So this is actually a very big field, and there's a lot of interesting mathematical structure there. But we should remember this is not a 1+1 dimensional field.
As far as non-locality of the correlators are, if you do something and then the operator is going back to the same position, it's not exactly the same operator. It's actually the operator appearing in another sector, say the Z2 odd sector or something. And in our description, actually include that. We we start from this Z2 even sectors, and then the complete description include all the 4 sectors. Z2 odd under the icing symmetry, Z2 odd under the dual icing symmetry, and another sectors. So indeed, in our description, we include all the 4 global sectors.
Yeah, but the correlation functions are non-local.
Yeah, the correlation functions from one sectors can be mapped to another correlation functors under some operation to the operators in another sector in the same position.
The correlation function is not a function of the position.
It's a function of it has 2 index. It has which block is this, and it has a position.
And that's not enough, because if you take, say, z goes to e to the 2 pi I z, you end up with a different answer.
You end up to another local sector operator in another global sector.
But that means that the correlation functions, fix an operator, and you ask what happens to the correlation functions as you change the position. They are not single valued.
Yeah, it's like you have many Riemann sheets when you just map to another sheet.
So the correlation function is not a number. If you put this thing on the computer and you compute, you get a number or not?
You get a number, you get a prefactor.
No, you don't get a number because the answer is not well defined. You have to say which sheet you're on.
Which sheet is also a number.
Look, I think there's a huge body of work about the study of these correlation functions, which are not single valued.
That I agree. We surely haven't know how to pin down all the correlation functions.
You don't have sensible correlation function. Look, I can go even earlier in history. There's a paper by Kadanoff and others, where they considered in the Ising model correlation functions of sigma, the spin field, and they asked what happens if we also want to throw in the disorder operator, right? So people said that they wanted condensed matter people. So here is a condensed matter physicist. I think he's a certified condensed matter physicist, Kadanoff. And what he said, and I think somebody even referred to him today. So you consider correlation functions of many insertions of sigma, and you want to insert the mu also, the disorder operator. Mu does not exist as a local operator. If you consider the correlation functions, you're not going to get sensible answers. Instead, what you should do is attach a line to mu. Mu is an operator at the end of a line. So sensible correlation functions are insertions of sigma and insertions of mu's, which are connected by lines. And as you start taking sigma around mu, you will see that the correlation functions are mapped to another objects like this, but the lines are in different places. So the upshot of all that is that the mu itself is not a local operator. It's at the end of a line in 2 dimensions, in 1+1 dimensions. So the sensible correlation functions are points for all these insertions of sigma, points for mu, and you also have to specify where the lines are in 1+1 dimensions. All this was already in Kadanoff's paper. The more modern perspective offers another thing you could do, attach it to a bulk. There's a 2+1 dimensional bulk attached to the system. And using the bulk, you can take these lines and run them through the bulk instead of running them through the boundary. But it's still the same physical picture. If you want to consider all these operators, both sigma and mu, both the order and the disorder, you have to keep track of the lines. Otherwise, it makes no sense. And all this was understood in the 70s and 80s before most of you were born. So I don't see why we need to go through this. I need coffee. Who is the chairperson? Is there another talk today?
No, I think this is the end of it. Lucy was the host. I don't know if she's still.
Yeah, all right. So if there are no additional questions, let's call it a day then.
Yeah, thank you.
Thanks everyone.
Nice talks, both of you.
Thank you. Bye.